Hello viewers, welcome to EF. Today is the 10th video of IT security complexity theory part. Today I'd like to discuss about the runtime complexity. So what is runtime complexity? We know that every algorithm has input, output and finiteness property. So the runtime complexity of an algorithm for a given input size is measured in terms of number of steps it takes before it terminates. What it means? We have algorithm for that we are giving the input size and that is measured in terms of number of steps it takes before the algorithm terminates. Okay, so now the runtime complexity types. The first one is worst case, that take the maximum number of steps to take the algorithm terminate for a given input size. Now the best case, which takes the minimum number of steps for an algorithm to terminates. And the third one is called the average case, which is the average of worst case and the best case. Now always measured as a function of the input size of n. What is that? Let's say a particular input W which has a string BAAC BAA. The length of W is 7. So the n is equals to 7 here. That is the input size. So we will consider always for the runtime complexity f of n. So now what is polynomial time complexity? It's very simple. The polynomial time complexity is the worst case or upper bound of a function of the steps of an algorithm that needs to take to terminate for a given input size as a polynomial function. So the input size will be polynomial function. Why? We will see it in the definition of big O notation. So now there is another question. What is problem complexity? In the problem complexity we always consider the best case. Means problem complexity is the complexity of the best case algorithm that can do the job. So problem complexity means that which one takes the lowest number of steps. Okay, so when we will see the big O notation you will understand what I mean. So let's see. Yeah, so big O notation, maximum runtime of an algorithm for a given input size. What is the upper bound or worst case of a function is called big O. If the input size increases, then the running time of an algorithm is also increases. So let's see the example. Let's say that for a problem we have three type of equation solve, A, B and C. For A we get order of n. For B we get order of n square. And for C we have this order of root over n. In these three equations, we always pick the best case, that is the smaller equation. So in this case C is the best case, smallest problem complexity. For the same problem we have the C we will pick up, but in big O we have the equation order of n square for b and c is different and a is different. So I hope you understand. So another problem, let's say we have two equations. For the big O, we will get the time complexity, polynomial time complexity we will get for a 3n square plus 15n minus f, we have order of n square. For b we have 15n plus something like it's a linear equation, so you get order of n. So compared to these two equations, what is the problem complexity of it? We always pick the smallest one. So the better one is order of n. And there is another important thing. If you have constant in your equation, for big O, you will not pick those constants. So if I have in the 3 example where I have this order of 5n plus 1, in that case I have to pick up only n for big O. Now mathematically we use asymptotic notation to describe this runtime complexity of algorithm. For that we use 3 symbols: big O, theta and omega. We know that big O, this is the formal definition of big O. So big O, worst case, let's see, we have a function f where we have n2 maps n till infinity. In that case we will consider the same order of growth or less is given by order of f of n is equals to some other function like g of n that maps to n to infinity. In that there will be some constant c1, c2 which belongs to natural number such that all of n is greater than n. In that case we have g of n is smaller than c1 f of n plus c2. We have this omega notation where let's say f is a function and we get the omega notation where g is a function such that we have some constant c which belongs to n naught and n naught belongs to n such that n is greater than n naught. We have g of n is greater than c of f of n. And there is the theta notation which is the average of both time complexity. That is the equation for theta of f of n. And then we have this g function such that there are g belongs to f of n and also g belongs to omega. So now there is another question: which growth is preferred, linear, polynomial, factorial, or what and why? Explain. So we have seen that the problem complexity always want to have a lower type of complexity. So that is our expectation, that always we will have a less complexity. Linear is better, but we can also consider that okay, polynomial time complexity is an algorithm is already acceptable. But there are also many problems which have the algorithm but their time complexity is not solvable in practical time, like TSP, Tower of Henry and others. We will see it in later videos. And even there are many problems are not solved yet. So we can see that here I already mentioned, like okay, the very first smaller is the linear equation and then that is expected, and after that we have polynomial equation, and exponential is greater than polynomial, and factorial is even worse than the exponential. So there are also constant and logarithmic time complexity. After that we have linear time complexity and polynomial time complexity, exponential, and then the worst case is